Aí ele estacionando o carro, ele falou assim, eu conheci você pela risada. Eu sabia
Nossa.
que estava por...
Uau! Nossa!
Característica.
Exato. Então não posso me defender.
Não pode,
mesmo,
né?
não.
Não tem como.
Tem que aceitar.
Ah.
Mas enfim, eu sou mais um dos alunos que a Catherine falou que está na Polônia.
Ah, legal.
Ah, legal, legal.
Sim.
Legal. Boa sorte aí.
Tô aqui sofrendo com frio e com essa língua.
É mesmo? É difícil?
Mas o pessoal fala inglês, não?
Não, aqui depende. Tem um corte generacional muito grande aqui, sabe? Se for uma pessoa tipo, com menos de 30 anos, 30 e poucos, com certeza. Ainda que seja um inglês muito macarrônico e tal, vai falar. De 40 para cima é muito raro uma pessoa falar. E tem essa faixa aí de 30 e 40 que talvez, sabe? Então, a gente vai mímica, vai palavras soltas. Não é que eu falo polonês, eu não falo nada, eu estou tentando fazer umas aulas, fiz umas aulas soltas, mas dá para entender algumas coisas, assim, sabe? E alguma placa que você lê, dá para você tentar entender.
Entender bom dia, obrigado e só.
Exatamente. E desculpa, eu não falo polonês.
Isso já é bastante coisa.
Isso é a frase que você tem que falar perfeitamente.
Isso já é bastante coisa.
Exato. Não, essa é a frase que eu uso que eu mais uso aqui.
Mas você consegue... A coisa importante
tá parecendo eu na França.
A coisa importante é saber como que eles colocam o nome nos banheiros. Você sabe ler feminino e masculino, isso é importante. Feminino e masculino,
né? Pois o pior é que tem um monte de palavras que eles usam para se referenciar.
Esse é o problema. Na Noruega, uma vez eu estava na biblioteca da universidade e fui para ir no banheiro. Eu parei na porta, eu já tinha ido a outros banheiros no instituto, etc., mas no banheiro da biblioteca eles usavam outras palavras. E eu olhei assim, gente, eu sou isso. Foi
é tipo assim, ele e ela, cavalheiros e damas.
Masculino e feminino,
masculino
homem,
e feminino.
Senhor, senhora.
A gente também deve causar esse tipo de problema para eles.
Sim,
né?
E aí, o que é isso agora, né? Não fazia ideia.
Nossa,
eu fiquei um tempo na porta esperando.
O lado bom
o Diego
botou
aí. O bom da Polônia é que todo espaço métrico é separável.
Polish Space.
Muito bom, Polish Spaces. Não, eu confesso a vocês assim, eu até estudei um pouco de francês e tudo, e gosto muito da língua, e entendo muita coisa, mas para falar, para articular, é muito complicado para mim ainda, porque eu não tenho hábito, né? Aí lá vou eu para a França, para o congresso.
Não, mas o francês eu consigo até levar de boas, assim, porque a raiz é a mesma, a estrutura é a mesma.
Eu acho que eles preferem que você fale francês errado do que você fale inglês com eles, porque eles ficam muito pirados quando você fala inglês com eles.
É verdade.
Eu pedia perdão e dizia assim, je ne parle pas français encore. Aí dizia, can I speak English with you? Aí eles
quase suplicando, né?
Pelo amor de Deus. A maior sorte que eu dei no planeta foi quando eu cheguei numa padaria e era de um português.
Pronto,
aí eu fiquei feliz da vida na França.
Falando em
Olá,
português.
Pedro.
Não, fala português.
Só falando de português. A Luciana acabou de falar de português e você apareceu, Pedro.
Oi, Pedro. Tudo bom?
Bem, Luciana.
Tudo bem.
Pior aqui do lado da casa do Gladstone tem o Café Lisboa. De coisa portuguesa. Aí você vai crente que vai ter alguém falando português naquele lugar. E ninguém fala.
Aí é muito engraçado, porque você pede I would like to have a espresso and a pastel de nata.
Pastel de nata. Muito bom.
E eles entendem?
Porque se falar...
pastel de nata?
No menu tá
o nome, tá no menu.
No menu tá pastel de nata.
Tá escrito em português.
Tá escrito em português.
Mas se você falar pastel... Que nem carioca,
eles entendem.
Pastel ainda entendem? Pastel, porque o carioquês vem um pouquinho do português de Portugal, né? Então faz sentido pastel de natas, tem que fazer o de natas.
De natas.
O Pedro tá dando risada na cara da gente.
So for the foreigners,
imitando português, né, Pedro?
For the
Você tá
foreigners here,
autorizado.
we are going to change soon for English.
Oh yes, I think it's better to speak English now.
Yeah.
Yes.
We tend to start with our language, but
2 minutes to begin, or
you are the boss, but I think it's better.
I'm the boss. Okay, everybody, mute.
And maybe you want to make me co-host?
Oh, sorry. I think I will never, ever remember this. I have to do this every talk, and I will never be able to.
Yes, put me as co-host, please.
Yes.
Hello, everybody.
Hello, Alexander.
Hi, Alexander.
Okay, Davi, we keep going, speaking Bayanese in English.
Thank you.
But everyone speaks English with some kind of accent, I guess. What I like most is the Italians speaking English. I don't know if Zaire arrived already, but it's more melodic. It's the most melodic English.
I guess we sound a lot like it. We as Brazilians, we sound a lot like Italians. There,
I think so.
I did my PhD in Barcelona, and well, there you speak Spanish and Catalan. And whenever I would speak Spanish, people would think I'm Italian.
Ah, really?
Okay.
Because the way my accent.
Yes, the cadence.
Yeah.
I think I cannot hide that I'm Brazilian. Everywhere in the world that I went, people knew immediately that I was Brazilian. It's
in United States, it happens to me. When I was there, yes.
Yeah, for me,
everybody that I wanted. Oh, you are Brazilian. Oh yes, I'm a Brazilian.
Well, Isaiah told me that he can speak any language in just using his hands, you know.
That's a new level.
Yes.
I can imagine you giving a talk just using your hands.
No, it's like
that's Google, right?
Like how you speak jabuticaba in Italian. So, jabuticaba. You know?
Jabuticaba. And put your hands.
Exactly.
Yeah.
Is Isaiah here? Is Isaiah here?
I think he didn't arrive yet. We can keep making fun of him.
There was a talk by Lyson Young happening an hour ago, so maybe they still at the talk.
Okay. Do you want?
So here's another question that came up in the discussion of this. We know there's languages according to countries, but what about according to subjects? So at this conference, you have to speak the language of, what do we call it? Oh, stable ergodicity. But if you go to a number theory talks, you have no idea what anything is.
Yeah.
Not a clue. And then you can ask, how many math languages do you speak?
Yeah, that's a good question.
Yes, very good question.
Everybody,
maybe you should change this to a challenge. So we should increase the number of mathematical languages that we can speak.
Well, yeah, it's hard to do, but you know, people apologize. I'm going to talk about assuming you know the language of stable ergodicity, and everyone apologizes when they talk about the stable manifolds. Yeah, you can quickly figure out their language source.
There is a tricky thing that there are many words sometimes that appears in many languages that you think you know what the word means in mathematical language, but then you're completely off. Yeah. So you might hear this question, you think you understand what's happening, but then you don't because of these words.
Yeah, yeah.
Okay,
Like,
okay.
it can take many years, many years. I'm going to speak Italian now. Many years to understand when someone says a foliation, foliage, it's not smooth. It's C1 plus alpha. Whereas there are other people I know, you say foliation, it better be smooth. So.
Yeah.
I think like isomorphism is the same word for many things in different languages.
Yeah, yeah.
Yeah, you're right.
Okay, are you all ready? Are you ready?
Yeah, I'm fine.
Yeah, okay, let's go. And it's my pleasure to introduce Davi Obata on the last day of his mini course about stable ergodicity. Welcome, Davi.
Thank you. Again, I appreciate those that already have their cameras on. I always encourage those that feel comfortable with to have their cameras on. So today, actually, I want to explore a different world from what we talked about the other couple days, which is the world outside partial hyperbolicity. So a comment is that most works in stable ergodicity are done in the partially hyperbolic setting. A big reason for that is Pugh-Schub's program for stable ergodicity among partially hyperbolic systems. And the program gives you like a type of approach to look at these conjectures, which is to prove stable accessibility, that this property is dense, and then to prove the accessibility implies ergodicity. Okay. And when you talk about accessibility, usually you talk about accessibility for the strong direction, so for the stable and unstable leaves of the stable and unstable foliations. But a natural question is, what happens outside this world? What happens outside this partially hyperbolic world? And in this setting, the picture is a lot more incomplete. And the honest answer is that we don't know a lot of things. We just have pretty much examples and particular results. But we don't have a big picture like in Pugh-Schub's setting, in partially hyperbolic setting. We know, for example, among partially hyperbolic systems with one-dimensional center, stable ergodicity CR dense. We know C1 density of stable ergodicity for any center dimension. But here, it's a lot more incomplete, the picture. So let me give you two definitions to set up the world that we'll be looking at. The first one is called dominated splitting. So we say that a diffel admits a dominated splitting if you have the composition of your tangent bundle such that you verify this type of inequality for some uniform time. And this inequality states that if you see, you don't know if E contracts or F expands, you don't know any of that, they don't have to. But what you do know is that if you see some expansion in the E direction, you need to see a stronger expansion in the F direction. And if you see some contraction in the F direction, you need to see a stronger contraction in the E direction. So this is one thing. And another thing is what we call weakly partially hyperbolic, which is the case when you have a dominated splitting, but one of the directions is actually uniformly hyperbolic. So you can have a dominated splitting of this type, ES plus F, or of this type, E plus EU. And here, usually when I talk about partial hyperbolicity, we assume these two bundles to be non-trivial. In the weak partially hyperbolic case, the idea is that you could have one of these bundles could be trivial. One of the hyperbolic bundles could be trivial. And a comment is that, well, if you look at those two bundles together in a partially hyperbolic splitting, then you would have, you can look at this system as a weakly partially hyperbolic one. or if you look at these two bundles together, you can also look at the system as a partially hyperbolic one. And the thing is that partial hyperbolic systems are contained in the weak partially hyperbolic ones, which are contained in the dominated splitting ones, the ones that meet a dominated splitting. But you do have examples where a weakly partially hyperbolic system is not partially hyperbolic, in a system that has dominated splitting, but it's not weakly partially hyperbolic. So you have this type of thing. So I'm gonna give one of these examples in a few slides. Okay, but you have these possible structures that are more general than just partially hyperbolic. And so you may wonder about stable ergodicity. And I mentioned before that you can look at stable ergodicity in terms of C1 stable ergodicity, C2 stable ergodicity, and things like that. But if you're looking at C1 stable ergodicity, meaning a diffel, conservative diffel that is stable, that is ergodic, and every C2 diffel that preserves volume in a C1 neighborhood of this diffel is also ergodic. Well, by some results of Arbieto, Mateus, and Teixeira, you can justify that C1 stable ergodicity implies some type of hyperbolic-like behavior. And this is dominated splitting. So C1 stable ergodicity actually implies dominated splitting. So if you're looking to study stable ergodic system, you need to be at least at the dominated splitting setting.
So does that because they can build counterexamples if the foliations aren't well defined?
Well, you don't need to have foliations now. If I go back here, dominated splitting, you have two directions. They don't have to be hyperbolic, so you don't even need to have foliations tangent to them. But so this is similar to I think is the same type of philosophy that robust transitivity implies dominated splitting. And here, if you're in a volume preserving setting, you change robust transitivity to stable ergodicity, then this also implies this dominated splitting.
Okay, thank you.
Okay. But yeah, the directions, they don't have to be integrable. You don't need to have foliations tangent to them. Okay, so you have this type of structure. Well, a first example of a stably ergodic system, which is not partially hyperbolic, appeared so this is a famous paper of Bonatti-Viana in 2000. They study more general things. They study what are called U-states or U-Gibbs measures. But at some moment, they construct some examples that are volume preserving. And in one of the examples they construct is actually stably ergodic, and it is weakly partially hyperbolic. So it has one hyperbolic direction. So this happened in 2000. In the same paper, they construct a different type of example, which was robustly transitive, and it had no hyperbolic direction. So it had only a dominated splitting. And they asked the question if that example was stably ergodic. And in 2004, in Ali-Tazibi, in his thesis, he actually proves that the other example that appears here is a stably ergodic. So he actually, so he gives an example of a system that is stably ergodic, but it doesn't have any uniformly hyperbolic direction. And this is pretty much the only example we know. Okay, I'm going to explain not exactly the construction of this example, but this type of constructions to obtain this type of examples, but in a specific setting. Okay, so those are the first examples of stably ergodic systems that were not partially hyperbolic, meaning they did not have both uniformly hyperbolic directions, and in the second one, you don't even have any uniformly hyperbolic direction.
Excuse me.
Yes.
What is the regularity of these examples?
So they can be made to infinity if you want.
and
Yes, so maybe
stably ergodic in which regularity in C1 for C1 perturbations or for
so stably ergodic means the following: there exists a C1 neighborhood of your system such that any other system in this neighborhood, but with higher regularity, so at least two, that preserves volume, is ergodic. So you look at the systems with high enough regularity, but they only have to be C1 close.
I see.
Okay. All right, so let me give you some results in each of the settings. So one is dominated splitting. The other one is weakly partially hyperbolic. So a first one, dominated splitting, that I mentioned, is you have this result by Alitazibi, where he gives an example of a C1 stably ergodic system with no uniformly hyperbolic direction. So here you can think you have a system with a decomposition of this type. So you have two bundles, but it's not, none of them are uniformly hyperbolic. And what I can prove, I give a criterion for stable ergodicity only with dominated splitting, but adding an additional hypothesis, which is a type of topological hyperbolicity that it's called chain hyperbolicity. I'm not going to define here, but it's just some type of topological hyperbolicity. And with this criterion, this gives me more flexibility to construct Alitazibi's example, but it's still the same type of example. It just says that you can, in Tazibi's construction, you make some deformation of an Anosov system in a small ball. With this criterion, you can make this ball like large, not in measure, but in size. But it's not a ball, but like a cylinder. But anyway, but it's pretty much the same example. You just change a little bit the construction. But one comment is that this example is what it's called a derived from Anosov, which I will describe in some pictures in a few slides. And in particular, they are isotopic to Anosov systems on the torus, these ones that we construct. So a natural question is, does it exist an example? Can we find an example, such example of C1 stable ergodic system with no uniformly hyperbolic direction, but which is not isotopic to an Anosov system? So this we don't know. And at the moment, I have no idea how you would go about constructing such type of example, but anyway. Okay, so this is pretty much what we know in the dominated splitting setting. If you add more structure, so in the weakly partially hyperbolic setting, well, you have this first example by Bonacci-Viana in 2000 that gives a C1 stably ergodic system with only one hyperbolic direction, so you don't have ES and EU. In this case, you have only EU, for example. In the same work for the dominated splitting, I can also give some criteria using that topological type of hyperbolicity to prove stable ergodicity. And that also allows me to be more flexible in the construction of Bonacci-Viana, but it's still the same type of example. It's just a little bit more flexible. And then you have another recent work by Gabriel Nunes. He was a PhD student of Hannah Rodriguez-Hetz. And they studied the properties of what happens. So in this setting, you would have, for example, ECS plus EU. So in particular, you have, so this is uniformly hyperbolic direction. And in particular, you have a foliation tangent to this. So they explore the consequences of this foliation being minimal. So they proved that if you start with a C1 generic D-fill in dimension 3, among volume preserving systems, C1 generically among volume preserving systems, the minimality of this foliation implies C1 stable ergodicity. Okay, so they explored this property of minimality of the strong foliation. Okay, and then in a recent work, we kind of joined force since we're thinking about similar things, and then in a recent work with Gabriel and Hannah, what we can prove, we give new examples of C1 stably ergodic systems which are weakly partially hyperbolic. So they only have one hyperbolic direction. So I'm going to state the precise theorem in a little bit, and then we're going to look at this theorem with a specific construction in mind. Okay. All right, so this is pretty much what we know in outside the partially hyperbolic setting. So you can see we don't know much. There's still a lot. It's still very mysterious, this world. We don't, I mean, we just have pretty much examples and a few results, but we don't have a good global picture of what could happen in this world. So, which is quite different from what we expect in the, it's a lot more structured, this type of theory in the partially hyperbolic setting. Okay, so let me state one theorem. It was proved first by Hannah Rodriguez-Hertz in dimension 3. And then it was, you have a general version in any dimension by Avila Crovisier Wilkinson, which is the following dichotomy. So every time I talk about C1 generic, you think of what's called, so you think of D-fills F belonging to some set inside the space of D-fills of regularity C1 that preserves volume here. And this set R is a dense G delta set, subset. So it means that you can think of this as being like a typical D-fill in diff1. So there is the following very nice dichotomy. If you pick a generic system with regularity C1 among volume preserving systems, one of two things happens. Either all the Lyapunov exponents of this system are zero, all the Lyapunov exponents with respect to volume measure. So almost every point, all the exponents are zero. This implies that you have zero metric entropy. So either you have zero metric entropy, or all your exponents for almost every point are non-zero. So you are non-uniformly hyperbolic. Your volume measure is actually ergodic. And the Ozeledet splitting, it's what you call dominated. So yesterday I explained that Ozeledet theorem gives you these bundles that they are only measurable. So it could happen that their angles between them could degenerate and go to zero. But generically, C1 generically happens that the bundle with the direction with negative exponents, the direction with positive exponents, they actually have a control angle between them. So they actually admit what we call a dominated splitting. So this is the picture C1 generically. And just a comment, in this world here, we don't know much, not much known in this part. So it's to understand what is the dynamics in the part that you have zero entropy. But here you get that C1 generic systems are ergodic. So a natural question is to know if you can promote this ergodicity to something stable. So it's conjecture in the paper by Gabriel Núñez and Hannah Rodriguez-Hertz that you can promote this second part to stable ergodicity. And another conjecture is that in dimension 3, you have a special structure because of the low dimension. Actually, in dimension 3, you can prove that if you're in the second case, you actually have at least one hyperbolic direction, uniformly hyperbolic direction. So in dimension 3, if you're in this case, in dimension 3, then you have a splitting of this type, for example, or of this type, where you can guarantee that this has dimension 1 at least. So if you have a hyperbolic direction, uniformly hyperbolic direction, you have the foliation of this direction. And they conjecture that C1 generically, in the case that you're in this setting, in second case, if you have positive metric entropy, then this hyperbolic direction, well, it induces a foliation, and that this foliation is minimal. So there exists a minimal unstable or stable, if you're in this setting, foliation. Okay. And this goes along with their result that explores the minimality of the strong foliation. If they had minimality, they can say that you have a stable ergodicity. So if you knew this minimality of these foliations generically, you would get stable ergodicity generically as well. Okay, but we're
they assert that the foliation is one-dimensional or not?
So it's at least one-dimensional.
Okay, at least. Okay.
Yeah, if it's not, then it's even better. But if it's at least one dimension, that's enough. Oh, I mean, that's you know that you have at least one foliation with dimension 1. Okay. Yeah. So this we're still pretty far from these conjectures. As far as I know. So our theorem, which gives the new examples, is the following. In the isotopy class of any volume preserving partially hyperbolic diffeel of a 3-manifold, you can find a C1 stable ergodic system, which is not partially hyperbolic. So in this setting, our system would have to be either of this form or of this form, where this direction, this bundle here, is not decomposed any further into like a hyperbolic bundle plus a center part. Okay, but you can do this in the isotopic class of any partially hyperbolic diffeel. So you could start, for example, with the time-on map of the geodesic flow and things like this. You could construct these diffeels. And the goal, so one remark is that the proof of this theorem uses a lot of C1 technology. So one thing that you can keep in mind is that we know a lot more how to perturb things C1. We see R perturbations with R greater than 1. It's really difficult usually. So in this case, we use a lot of C1 technology to conclude this theorem. So it's a C1 type of result. But the goal is to explain this theorem with a specific example in mind. And it's an example that I like a lot because it's how I got into studying stable ergodicity many years ago. And yeah, so it took a long time to figure out how to prove stable ergodicity of the example. So the example I want to describe is actually a derived from an Nosov system, what we call a derived from an Nosov system. So let's start here. You fix, for example, a linear Nosov diffeel in T3, and you suppose that it has 3 directions. You can decompose the hyperbolic split into 3 directions. You have a stable direction. You have a weak unstable, so it's a direction where you see a weaker expansion. And you have a stronger direction in the unstable part, so a direction where you see a stronger expansion. So the idea is to make a DA type of construction in which you obtain a diffeel G with a decomposition of this type, where this bundle here, you cannot decompose any further into dominated splitting. So let's start on this part of the picture. So suppose you look, so okay, my drawing is not very good, but suppose you have here a fixed point, and then this is how your picture would look like for the initial Nosov system. So you have a strong, unstable, a weak, unstable, and a stable direction. So Magne introduced this type of constructions where you can deform your Nosov systems and create more complicated things. So at a first moment, what you do is that you bifurcate this point into 3 points in a way that, so you have those 2 points on the left, on the right. They still have an expansion in the center direction here. So let's call this direction. Let's call this direction for the moment EC, just so I can say center direction. So you still have an expansion, a weak expansion in this direction. But when you do this, you can create another point in the middle where you switch the behavior in the center direction. Now the behavior is contracting. Okay, and you still have a direction that you see a stronger expansion, another direction that you see a stronger, a stronger contraction, another direction that you see a stronger expansion. All this picture, you should think of all this picture as being contained in a very small ball. And everywhere else in your manifold, you keep your Nosov system. So you have an Nosov system pretty much everywhere in your manifold, except in a small ball where you did some deformation. So you create this new point here, with index 2, stable index 2. And now the idea is that you want to create a complex eigenvalue for this point to mix those 2 directions around this part. And what you get at the end, it's something like this. So in a smaller ball, you deformed again to make a direction with complex eigenvalues so that you see some spiraling around this point P. So this happens in a smaller ball here. And the other points, they keep having the same type of picture as before. And when you do this, what you're doing is that you're mixing the stable direction with the center direction around that fixed point P. At the end, what you will get is a system with a decomposition of this type. And this center stable direction, you can think of this as corresponding to this center plus stable direction, but you cannot really decompose this any further because you mix those 2 directions together around this point P. So this is a genuine 2-dimensional center stable direction, and you have a 1-dimensional unstable direction. And when you do this, let me just mention, you do this deformation in a small ball or in a small set containing this periodic point P, this fixed point P. And everywhere else in your manifold, you kept the same structure as you had in this picture. So if you think of this picture as in the torus, so I'm drawing the torus here as 2 torus, but you should think of this as 3 torus. You did something in a very tiny ball here where you mix things, and everywhere else you have 3 directions. Let me put in quote marks. Okay. So this is the example to have in mind. I'm going to call this fixed point here. So we obtain a difffield G as we do this type of deformation. And I'm going to call this fixed point here where you mix things, and this fixed point where you have index stable index 2, where you mix things, I'm going to call this P. Okay. So what our theorem states is that so you have this G. You can look at a small C1 neighborhood of this G. Then densely, C1 densely in this neighborhood. Every C2, so you have a C1 dense set of C2 diffils that preserves volume, such that every diffil in this set is C1 stably ergodic. So we don't know actually stable ergodicity of G itself, but densely in a neighborhood of G, you have stable ergodicity. And the reason for that is because we're going to use a lot of C1 technology. So my goal is to explain this thing with that picture in mind, or at least give like the main ingredients of the proof. So the first idea is we need a criterion for ergodicity. And on the one hand, we have this Hopf argument, and there is this Hopf argument. It was put in a nice way in a criterion by Hetzet, Stasibiuris, where they give a explicit way to look at these things as you try to prove ergodicity. So that's what I'm going to try to describe. And to do that, I need to introduce something called ergodic homoclinic classes. So our ergodic homoclinic class is the following. So if you have a diffil C2 regularity, volume preserving, and you have P, a hyperbolic periodic point, you're going to define two things: the stable ergodic homoclinic class, the unstable ergodic homoclinic class. So for the stable, which I'm going to denote with a minus, and I'm going to put the erg here for ergodic, it's the set of points in your manifold such that the passing stable manifold of this point intersects transversely the unstable manifold of the orbit of the periodic point P. So you have some transverse intersection. So you have a fixed point P, a periodic point P. You look at its unstable manifold, and then in your manifold, you look at all the X such that the passing manifolds of these points intersects transversely these unstable manifolds. And you collect all these points, and you call this stable ergodic homoclinic class. The unstable ergodic homoclinic class, it's similar, but now you're looking at the stable manifold of your periodic point, and you're looking at the points whose passing unstable manifolds intersects transversely. And you put all these points in this set. And the ergodic homoclinic class is the intersection of these two sets. So far, this is a mysterious object, but I'm going to state a theorem that's going to make, it's quite nice to see this object after that theorem. So the ergodic homoclinic class is just the intersection of those two sets that I defined here. Okay, so this is a theorem that appears in the paper of Hetzet Stasibiuris, where they prove Pugh-Schub's conjecture for the C1 topology and systems, partially hyperbolic systems with center dimension 2. And the idea is that they just combine Hopf argument in a nice criterion in a way that you can kind of localize with quote marks where you're looking for your intersections. So this is done in the following way. So you have a C2 diffil, P, a hyperbolic periodic point. Then so we have the stable ergodic homoclinic class, you have the unstable ergodic homoclinic class. So you need those two sets to have positive measure. So this is the hypothesis. Those two sets that I defined, they need to have positive measure. And the conclusion is that your ergodic homoclinic class, and recall that the ergodic one was the intersection of the other two. So it actually tells you that this set coincides with any of these two up to a set of 0 measures. So this equal with a circle on top of this is just that up to a set of 0 measures. So this tells you that those 3 sets, they coincide. And it also tells you that this set describes an ergodic component of volume measure. Okay. Okay, so with this thing in mind, you can think of a strategy to prove ergodicity for a diffil in the following way. Step 1, you want to verify the hypothesis of this theorem. So you want to verify that those 2 things, they have positive measure. Step 2, and here is the good thing when you have this equality, because you can just work, if you know that both have positive measures, then you can just try to work with one of the 2, or maybe the union of the 2. So step 2 is to say that you want to prove that either this thing has total measure, or the unstable ergodic homoclinic class has total measure, or the union of the 2 have total measure. Because then with this step here, you know that it's an ergodic component, but it would be an ergodic component with total measure, so your measure itself will be ergodic. So a good, I think it's nice in this clear form with this result, because then you can think of your problem as trying to work either with one of the sets or the other, or the union of the 2 to go to prove ergodicity. And this is the strategy we'll explore. Okay, so a first step then, we have our diffil G. A first step then is how to verify this hypothesis for some perturbation of G, not necessarily G. So this uses a lot of C1 technology. So we started with our point G, and we had our point P, which was the point where you had this complex stable thing happening. So for perturbations, this is a hyperbolic point, periodic point. So for perturbations, I'm gonna denote with a sub-index just to say that is the continuation of this periodic point, of this fixed point, depending on the diffil. Okay, so we started with G, which was a D8 system on TT3, and we had this decomposition, ECS plus EUU. And PG was the periodic point with index 2. Now, I put together here a bunch of results and consequences for C1 generic systems by Avila Bocchi and Hannah Rodriguez. What happened is that you start with your G, then you can jump to a diffil F that I'm calling F gen for generic, which is C1 generic. And this diffil has a lot of good properties. For example, we know that volume is ergodic for this diffil because it has positive entropy, because it started with a decomposition like this, so you have robustly positive metric entropy. So this would, in the dichotomy that I stated before, this would imply ergodicity. You also know that the system is non-uniformly hyperbolic and Ozella is dominated. This implies that the exponents in this direction have the same sign because Ozella splitting is dominated. So this implies that for almost every point, both exponents in this direction are negative. Another thing that actually comes from this Avila Bocchi part is that, so I define ergodic homoclinic class for C2 diffils because I talk about pacing stable manifolds and unstable manifolds, but you can also define the set in this for C1 diffils if you have dominated splitting, plus because pacing you can construct pacing manifolds in the C1 for C1 diffils with dominated splitting. So you can still define those objects. So you would get that the ergodic homoclinic class of the point, the continuation of the point here is actually everything. And there is a semi-continuity property that also follows from Avila-Bocchi, which is the following. For every epsilon positive, if, well, you fix some epsilon, right? But if F is sufficiently close to this generic diffil with regularity C2, then if you look at the ergodic homoclinic class of the continuation of that point, it has measure 1 minus epsilon. And this part actually goes along with a comment that Alexander made on the first day about an argument of this type, of saying when you have an ergodic component, you have some type of semi-continuity of this ergodic component generically. This is how you can look at this point 4. So a conclusion of this thing is that for C2 diffils sufficiently C1 close to the generic one, both parts of the ergodic homoclinic class, the stable and unstable ones, have positive measure because of this condition here. So you verify the hypothesis of the criterion, which asks just to have those two things with positive measure. So if I go back here, so here we needed those two things to have positive measure. Then now we know that for C2 diffils close, C1 close to the generic one, those two things would have positive measure. So I can play with this game. So in our setting, we have for a diffil F close to the generic one, you have PF is the continuation of that fixed point. And this ergodic homoclinic class, the unstable ergodic homoclinic class, since you have a strong hyperbolic direction, it's actually translated to the set of points whose unstable leaves, whose unstable manifolds, intersects transversely the stable manifold of PF. And the main goal then is to prove that this set has total measure. Because if we do this, then we would know that the ergodic homoclinic class of PF would have total measure, and this is an ergodic component. And this implies ergodicity for diffils F. So for every diffil F sufficiently C1 close to this one, you want to verify that this set has total measure. And the enemy is the complement of the set. So for each diffil F, you may just look at, I define this gamma F as the complement of that set. So luckily, since we're dealing with a measure here, to prove that this thing has total measure is equivalent to prove that this thing has zero measure. Okay. Yeah, so the main proposition follows from proving that this thing has zero measure. So we're actually studying the structure of this thing. So a few comments here is that this set has the following nice properties. First one is that if I go back here, this one is easy to see. You have PF, you have the stable manifold of PF, and you're looking at the points whose unstable intersects transversely this stable manifold. This is an open property because this comes, you have a nice unstable foliation. So this means that for any point close here to X, since these unstable manifolds will be close to each other, they will also give you a transverse intersection. So this set here will be open in our setting, which implies that this set is closed, so in particular compact. So you have a compact set. You can also prove that it's invariant and it's U-saturated. And that follows from the U-saturation. U-saturated means that it contains entire unstable manifolds. And that follows because the complement, you're looking at also entire unstable manifolds with the property. Other things, you have some type of semi-continuity. So this is upper semi-continuity, which means that if you take a sequence of D fields converging to someone, the lim sup of these compact sets, gamma Fn, it will be contained in the gamma F. And another thing is that in our setting, we had PF. We broke the partially hyperbolic splitting of this type. We broke this in a small neighborhood, which I'm drawing as a cylinder, around this fixed point. So this is the place where we broke the partially hyperbolic splitting. And you can actually do this in a way that this thing, it's contained, this part is the stable manifold. It's contained in the stable manifold of your fixed point. And these things contains your unstable manifolds, if you want. So since gamma F, it's the complement of the set of points that intersect the stable manifold of this fixed point, then gamma F, it's contained in the part where you still kept your partially hyperbolic structure. So you can actually prove that gamma F is partially hyperbolic as a set with a decomposition ESS, EC plus EU. And the goal then is to prove that if F is sufficiently close to the generic one, then the measure of this set is 0. And if that wasn't true, then you could find a sequence of C2D fields. So here, if F is C2, but C1 close to F generic, then you could find a sequence of D fields converging to F generic with positive measure. So this gamma F, it's U saturated, so you have this these unstable manifolds in it. And then this remark here is actually a consequence of a Hopf type of argument. The first part that I mentioned is that if you have a compact set invariant and partially hyperbolic for a C2D field, if this set has positive measure, then it contains stable and unstable manifolds. It's S and U saturated. And the idea is that this is invariant, so it will contain its ergodic components. For a typical point, Hopf argument tells us that the ergodic components are S saturated. And compactness will tell you that those things will actually coincide. So this is the type of thing you look for this thing, which will imply then that for these sets here, since they have positive measure, for every point, it will contain the stable and unstable manifolds of these sets, of this point. So you have a sequence of set, you may look at the lim sup of the sequence, and this gives you some subset of this thing here, which is SU saturated. So you have some compact set in the limit, which is SU saturated and invariant. The last mysterious thing I'll describe is that, I'll just state, is that whenever you have this, because the center dimension is 1, because you have one center dimension, Hannah, she proves that if you have this thing, then you can find 2 periodic points in this limit thing, which are connected by the strong manifolds. So you have here Q1, Q2. Here you have a partially hyperbolic structure, so you have a strong stable manifold for this point. You have a strong unstable manifold for this point. Here is strong stable, strong unstable. And here, oh, sorry, let's put the point there. Strong is stable, and they are connected by these strong manifolds. But you have the center direction. These manifolds, they don't, the dimension of these manifolds, they don't form full dimension. So, and this is happening for a generic D field. then you apply a Kupka-Ismail type of argument to say that this cannot happen. You actually, those things, they have to be in general position, because it's not full dimension. So a Kupka-Ismail type of argument tells you that this thing can happen, and this leads to a contradiction. So the sets, they had to have zero measure to start with. Anyway, so this is just to give a few remarks, is that we can construct similar type of, we can do this construction starting with any partially hyperbolic system. We don't know that the enemy, it's empty generically. We would know that it has zero measure. But if we did know that, this would imply minimality of the strong unstable foliation for some reasons. But we don't know this thing. The idea is that it was only sufficient to prove that this thing has zero measure for perturbed systems. Okay, so I just, in the mathematical part, I just wanted to finish with this picture where you can think of the world for stable ergodicity. You have the nominated splitting world, which is this big world. You have a smaller world, the partially hyperbolic one. You have a bigger one here, which is the weakly partially hyperbolic one. I wanted to point out that a lot more is known here. There are a lot of works. But those two other worlds is very unexplored. We don't know much about them, and it's honestly quite open. We maybe we don't have the technology yet to deal with a lot of the problems there, but is the stable ergodicity dense in these worlds? We don't know. And we don't know also how to approach this at this time. Okay, so this is the mathematical part I wanted to say. I wanted just to finish with a few words about UFRJ, since we're talking about its 50th year anniversary of the grad program. This picture is the picture of CT UFRJ. If you ever go there by bus, that's what you see when you go to the math department. And it's nice. It brings me good feelings. When it's very hot, maybe it's not so nice, but anyway. I wanted to just say a few words briefly about my experience with, in particular with dynamical systems at UFRJ in the grad program. First thing is that it's a really good place to learn because there are many seminars there. You have these Tuesday and Thursday seminars. You have EDAIs being organized. You have this Sextas Matemáticas. So there are many seminars. So you are exposed to a lot of mathematics all the time. Another thing is that they have actually a lot of courses on dynamical systems there. And I was looking through my documents to see which classes I took, and I could find at least these classes in dynamical systems. So my first class was Introduction of Dynamical Systems with Zeze in 2010. I took an ergodic theory in hyperbolic dynamics class, one with Samuel Senchi, another one Alexander in 2010. Then a few years later, there were classes on sectional hyperbolic dynamics by Carlos Morales, partial hyperbolicity by Alexander. I took classes in fractal geometry with Catherine in C1 perturbation techniques. There were also classes in foliations and things like that that are related with dynamics. So you can actually have a lot of classes in dynamics there in the grad program. You know, like that's something I really appreciate there because the professors in general, they're just so easygoing that you can talk with them with no pressure. You can have, it is very easy to talk with the professors there. And I was very blessed to have many great students around me, and you kind of mirror yourself in the other students as you're studying. And I saw many students doing a lot of good things, so it pushed me to like do better in my studies. But I guess the main thing I learned at UFRJ that I carry with me until nowadays, as much as I can, is the importance of interacting with others in the learning process. So there are informal seminars, working groups. I was always talking with someone and I was always learning from someone. And since then, I feel that became part of who I am as a mathematician, to always try to organize these type of things to have this same type of experience. Unfortunately, I realized that I don't have as many pictures as I should from my time at UFRJ, and I really think that Zeze should create a public library with all her pictures, because I just put some pictures here of some of the time I spent there. Overall, it's a very excellent place to learn and to work with dynamical systems. I was very fortunate to have very good influence from UFRJ. And these are some pictures of seminars, informal seminars, the PhD defense of Bernardo, and a conference that was organized at UFRJ. So I just wanted to finish today saying congratulations to everyone, especially the professors. I know it's a lot of work that they put into it, involved to create this great program and this great environment to learn. So thank you all.
I have a question.
Yes.
Can you hear? After that advertisement for the graduate program, you forgot the American factor, which is how much do they pay the graduate students?
That's a good question. It depends on the scholarship you have, but I think, I don't know, what is the PhD scholarship there now?
Better than student total? I don't know. Luciana, do you know?
What?
How much is the PhD scholarship now?
2,200.
Don't know. 2,000.
200 has
200, I think.
2,000 and something.
Yes.
But what?
2,200 something.
I mean, is that real? What currency are we in?
Real, yes.
Yeah, it's real.
I mean, the question in the U.S. is some programs pay a huge amount of money, $30,000 a year for the student. Other programs, oh yeah, wow. And others like University of Chicago, where Davi is, they are rich, filthy rich. Places like my school, UIC, struggle. They pay $18,000, but they take taxes and fees, so you're not living well. You're living very poorly. So the question is, do they support the students in a way that not only do you learn, but you live a little bit?
Well, I think if I can answer to you, it's we are not
I think here in Brazil the difference, the cost of life is huge. Depending on the city, on the region. Yes, so in Rio de Janeiro and São Paulo, this scholarship is certainly not enough.
Yes, I guess one important comment here is that it's not a lot of money, and I mean you won't be like rich or anything. You can survive, but you live, because the students they still have a lot of fun together. They still have a lot of social interaction with each other.
Yeah,
I feel that the students they still have a life.
Oh yeah,
and it's the same for everyone. It's national.
I graduated recently from the. I graduated recently from the PhD in Rio. Really, is the same amount for all the institutions. The PhD, the amount of 2,200, it's fixed for all Brazil, and Rio might be a little bit more expensive. But since I'm not from Brazil, but I think the quality of life in Brazil, and it's really good. Compared to Rio, the rents are expensive, but it's cheaper than Europe and other places, I think. And you have a good quality of free places to interact, like parties and the beach and many stuff that Rio gives you, that they are really fulfilling. The culture when you're not in lockdown.
Yeah.
I encourage everybody to go to Rio.
If you allow me to add, I think the point is that the definition of quality of life is different in different countries. So here a PhD student is not gonna save money, is gonna survive, but is gonna be happy in the sense that you have many friends and parties and enjoy math. So that's what we can offer. We can offer this. Money is gonna be
perhaps.
Sorry, Jacqueline, this is a romantic view.
It's not.
Exactly.
Lose the memory.
I think so. I'm sorry, Jackie.
It is a romantic view.
I didn't defend that a long time ago.
I think I'd be happy.
Yeah.
Yes.
Catalina
If you don't have,
recently.
go to the beach and it passes.
Oh, yes.
But well,
you go to Ipanema.
Yeah.
So as someone, just to bring a bit
everything okay.
Just to bring a bit of realism here, as someone involved with the graduate program at another university, actually science in Brazil is under assault. So who has a fellowship? The few students that do have a fellowship, I think they can have a reasonable life. And, well, they are students, so they are content with that. The more important is to have access to science. But unfortunately, there are very few nowadays that do have this possibility, and this number is continuously decreasing. So this is something I think it has to be known about the reality of life in academia nowadays in Brazil.
Yeah.
I don't think it's singular in the world, but it's especially dramatic.
Yeah.
I think
they can add to this.
That we are all we are all here. Marisa in the comments, she said that we cannot afford an own flat, and we have to manage to live with another student. I think that is a common thing. Even for me now, I'm a PhD. Still, that is the housing, and it's a global problem also. I think it's not only a problem in Rio for me, but since I believe it's the habitational problem, it's a global problem. And another thing that I wanted to say that I found it really good of doing the PhD in Rio, that really you have 4 institutions that are in that region. You have the Yapuki, that they are all well communicated and has a lot of people to interact. The better things than doing a PhD in Rio.
Well, I will keep my romantic view because we have to keep someone with a good optimist view.
Okay. Okay. Just ask you. Anyone else has some question for Davi? If not, we thank you, Davi, again, and keeping talking about.
I have one.
Okay, please, Alexander.
So there is this criterion to prove the ergodicity of the ergodic homoclinic class, right? So it's a component ergodic, right?
Mm-hmm.
It's an ergodic component.
Yeah.
But is there some criterion to prove that the measure inside the ergodic homoclinic class is mixing or even Bernoulli?
I think it depends on. I think you could do this if you had information about the periodic point. For example, if it's a fixed point, I think you can prove that it's Bernoulli. So if it's similar, I think it's a similar thing as having a topologically mixing for
yeah.
class.
I know for topologically homoclinic class, yeah. But
yeah, so you could think in the same way there, because you could talk about ergodic homoclinic class to some power. You know it's an ergodic component. Pacing tells you that up to some period it's Bernoulli. So you could look at some power of your D field and decompose into the ergodic components of the power, and these would be described by periodic points, periods of periodic points. Yeah, you can do that.
Okay, good.
Okay. Anyone else? More questions or comments? No? So we can thank Davi again for his beautiful mini course and the words about the UFRJ. And now we can discuss about the way of the style of life in Rio or in Brazil.
I guess you shouldn't start the discussion because we are running a bit late.
It is time to Zezé speak. Oh, okay. Yes. Please, Jacqueline.
I don't know, maybe give 3 minutes for people that needs to refill the water glass or something like this.
Okay.
Jacqueline, I have to test my system.
Yeah, yes. To give some time.
Excuse me, so.
What should I do?
Let's go, Zezé. You are co-host now.
Mm-hmm.
You enter.
I don't know what to do as a co-host. Don't tell me. My point is just oh my God.
Não se preocupa, Zezé. Só para você poder compartilhar.
Ok. Now to.
Você pode compartilhar sua tela se você é co-host.
Tela. Calma. Wait a minute, please. Ok.
Isso.
Já está aparecendo.
Right,
ok.
Right.
Pronto. And how is the audio? It's okay? You can listen to me? Okay. Okay.
So perfect.
So I'm Brad. I hope that my network, the Wi-Fi here, it's okay during all the time. I don't know. I'm a little bit.
Yeah, but looks good. The audio is good, and the image.
I changed places indeed.
Yeah.
In the morning I was in another place, and now I am in another room. Let's see. Okay.
Just 2 minutes, Zezé, for people to.
Eu estou aqui com as minhas pastilhas para
garganta.
Porque começou a falar, resseca. Enfim. Let's see. Deixa eu manter isso aqui conectado. Ai, energia. Oi.
I'm afraid to start any small talk, and we get into too much philosophical discussions. So maybe just.
Come on! The discussions are most interesting part, because I mean, Rachel pointed out on her post private.
Yeah.
In the U.S., money doesn't buy you happiness, and it also doesn't buy you your own apartment.
Yeah.
You're all students share. But what happens is
I am not sharing. I do have my own apartment.
You do?
Well, I did. Now I'm.
See, that's a luxury.
Yeah, well, I didn't know what else to do with all that money.
You can donate.
Send to us, please. Send to us.
Yeah,
they spend it.
For some students in Brazil.
We're willing to receive it.
They spend it in liquor.
But I was gonna add one more thing. And see, there's many students, unlike Brazil, because they're not hiring professors. So like UIC just hired 50 new graduate students to teach. 50 people in a class hired as teaching assistant, which means they teach classes. That's huge. When I was director of graduate studies, we would bring in 20 or 30 maybe per year. And then total is about 150. But now they don't have anywhere near faculty enough. US is not hiring faculty is what they're not hiring. And so then the students can't get someone to direct their thesis. So I directed thesis 5 years after I retired because there were still people wanting to do dynamical systems. But then you lose touch. You know, I do my work, but they don't know what I'm doing. So they don't want to. It's a funny, the US is screwed up right now. I don't know if it's unique that way, but anyway, just money doesn't buy happiness. A good advisor buys happiness.
Yes.
But luck there
But
also
all that money brings a lot of things.
Yeah, so money buys wine.
Come on,
okay,
babe.
but it is by wine. Good wine.
let me make a point here. So
in Brazil, you say you are complaining with your mouth full.
Yeah.
Or belly full. No, but I think it's important to note that it's needed some money to support the students. And this is what Silvio was mentioning, that right now it's horrible. The situation is really sad. It's really sad.
Federal University received one fellowship for the graduate program for the next semester, one PhD and one master's.
What university are you at, Susan?
I'm at PUC.
This is a special situation. I could talk a lot about this, but
it's
no,
private,
no.
yes.
Yeah.
But the funding, it's the same. It's from the national science, the equivalent of the NSF.
Yeah, well,
which is now not.
The student is isolated. You hire someone good, who do they talk to? That's always.
But anyhow, I think that we, as people here, says, we are part of the people that discuss poverty in a bar, taking some drinking whiskey and the caipirinhas and so on and so forth. And so the intellectual people that discuss poverty, how to say this, having all the. We are.
We invite the students. The students are invited.
I know.
Yeah.
They don't pay.
They don't pay. Yeah.
Oh, that's always.
But anyhow.
Okay. So let me get ready. Zezé, are you ready?
Não, eu perdi a caneta. Espera.
Okay.
Meu Deus.
So I imagine that everyone is back now.
Não, calma. Aqui, achei. Pronto. Tá.
So let me start. I think. Sorry. Okay. So it's my great pleasure to introduce our last speaker, Maria José Pacífico from Federal University of Rio de Janeiro. Zezé, as most of us know her. So she's a prominent member of our Brazilian community, mathematics community. She's currently the coordinator of our postgraduate program. And well, she has advised several students along of the years, also supervised various researchers, young researchers, postdoc. Well, it's completely undeniable that she has strongly contributed to the development of this program that we are celebrating today. And especially her devotion and dedication to the program, it's really admirable and inspiring for everyone. So I would like to thank her to accept the invitation, but most of all, I would like to thank her for all these years that she has devoted for the program and all these years that she's been work hard and tireless for develop and make it make it better. So thank you, Zezé, please.
Okay, many thanks for the introduction. And just to be honest, the title of this should be the title for the first part of my talk. And then I will have 2 more parts. In the second part, I will report some of the facts that, in my opinion, deeply influenced our program towards the achievement of its academical excellence in the last decade. And in the third part, it's a losing memory of old times and events organized and realized that the Institute, speakers, friends, researchers that once visit us, okay? And then I ask you patience because maybe I'll take more time than enough. I don't know exactly, let's see. Okay, and then I will start with the first part, that's the mathematical part of the talk, that I tried to be quite geometrical. I'll try to do no calculations. And this is about one of my last works in collaboration with Diego Barros, that was an ex-student, a formal PhD student, and Christian Bonatti. Okay, and then what is the goal? The goal is to exhibit an open set of flows with the same attracting block. And each flow in the set contains a unique Lorentz-like singularity, sigma, in U, and under a certain condition on the expansion in the unstable direction of sigma, the vector fields in an open dense set, subset of this big set, exhibit either a two-sided or a up Lorentz or a down Lorentz attractor, and the 3 cases appear. I will explain the terms here. Usually, what is the singularity? You have that, I'll try to do here, a Lorentz-like singularity. You have here the unstable manifold. Here is the stable. And the third one is like this. This is the singularity, and it's Lorentz-like. If all the eigenvalues are real, and it's like you have 2 stable directions here, and you see that you have this, you can see that we call, this is a central stable manifold that contains the stable directions of sigma, and this is the unstable manifold of sigma, okay? And what is a Lorentz? Lorentz, usually you can see as, you can just, will forgot this, and then you have this. Oh my God, okay. You have a cross section here, here, another one. Okay, and what is the usual Lorentz? You have somehow, you have this, the first return map. You have something like this here. And this means that, what is this? You put the unstable manifold of the singularity, it's going to this cross section here, and the picture for the first return map on this cross section is, the images are those pinched triangles. This is what we call a usual Lorentz-like, okay? But you see that we are in 3 dimensions, and then we have that this plane here, the stable, centrally stable manifold of the singularity can be considered as the upper part. This is the upper part. Let me change color. This is the upper part, and this is the down part of the stable manifold. And then we could think, okay, I can do this picture on the other sides. For instance, here, this have this cross section somehow, no. Okay, and somehow what this represents, you just forget about this. And now you look the picture on the other side, down, okay? And then the unstable manifold is going here, and the other one is behind and goes there. Then we call this, we could say it's a downwards, okay? More or less, this is the representation of what I mean by up and down Lorentz, in the sense that, okay, I have a singularity, I have the center stable manifold of the singularity that it can be splitted if you omit the strong stable manifold. It splits into components, the up and the down, and an up Lorentz means that the unstable manifold of the singularities indeed approach it only this part of the center stable, the upper part, and the down Lorentz approach the other component of the center stable manifold.
Sorry.
Oi? Yeah.
Is this the geometrical construction?
This is just what I mean by up Lorentz and the down Lorentz, in the sense that the stable manifold here, you have the stable manifold, center stable manifold is like this.
Okay.
And then you just split. This is the strong stable, and then this is the stable. Okay, then you have the upper part here. And here, okay.
No, isn't there a symmetry that if you change if you make a coordinate change, then the upper part gets the lower part? What is not?
Yeah, more or less, but it is just, no, the point is just to explain what I mean in some sense. I will give you the construction with the beautiful pictures that indeed Diego was the author for the pictures, because they are really fantastic. I don't know, I hope that you can understand what is this. Okay, I will not erase this. And now up and down, it's just, I am repeating what I said in the first before, and the Lorentz-like means that the real eigenvalues are real and satisfying this condition here. You have the strong direction under the other one. Up. This you call the centrally stable separatrice, or stable separatrice of the singularity, strong stable separatrice. This is in the direction of the strongest stable eigenvalue. Up means that the attractor that I try to construct is disjoint from the lower stable separatrice of sigma. And what's the lower? The lower, I'm just considering this CS gamma less this. It's just the union, no? This CS plus union CS minus, no? Like I explained on the other, you have this is the positive and this is the negative, okay? Down is disjoint from the other one. And the two sides means that it should intersect both ambidextrously. No? That is the condition that what I plan to go. Okay, how we do this? Let's see. I have to start with the geometric Lorentz attractor because the constructs will really mimic this kind of method, okay? And what is the geometric Lorentz attractor is that it's a model to the flow generated by Lorentz equations. Lorentz equations are these ones. And the Lorentz arrived to this kind of equations, trying to model long-term forecast. And what was amazing is that, okay, this equation is a simple pair of equations, that polynomial, 2-degree polynomial equations, but at that time he could not solve the solutions, to give the explicit solutions. And with a computer at that time in the 60s, he could plot the solutions of these equations, and he conjectured that the solution should contain an attractor, volume is 0 attractor, and there should be an attractor, and sensitive respect to the initial conditions. Okay, but at that time it was impossible because it was quite resistant to the real solution of these equations, because you see that the orange here is a singularity and it's not hyperbolic. And then it was quite hard, and moreover, since the trajectories, the regular trajectories accumulate the singularity here. Indeed, it has this is a Lorentz-like singularity like this. If you, oh, excuse me, if you from the point of view, numerical point of view, you have just the errors accumulated in this as you approach the singularity. Then no solutions at that time. And then Guggenheim and Williams, they just proposed a model to this, and what nowadays is called the geometric Lorentz attractor. And the configuration of this model was like that. You have presents that singularity, and you start really the flow in a neighborhood of this singularity is linear. And then you just make a push and some expansion and the translations, you just return it to this cross section here as this picture here, okay? I'll take a color here. Okay. What are the main features of this picture here, or this model? Was that the existence of an invariant contraction foliation. In this picture here, they assumed that that was absolutely fundamental to Guggenheim and Williams verify the solution of the conjecture by Lorentz, that the existence of a foliation here, in this, which is invariant by the flow. You know that if we start nearby the construction, since this singularity and the flow, they put it linear, clearly from here to here, this foliation is preserved. But what they really assumed is that through this way to return to the cross-section, let's sigma, you will still preserve this foliation. And then what you see in the cross-section, you have this, you have the foliation, and the image is preserved. Okay, the image of each leaf goes to a leaf, to a vertical line in the image, okay? Well, why this is good? This is good because then you can just, it's like this, you can just project this in the space of leaves, and then you have a one-dimensional map. And you can study, this is like the following problem. Okay, I am in three-dimensional, and then if I have some foliation invariant, I can simplify the dynamics and see in a two-dimensional system. And the projecting, I have a one-dimensional system. And it turns out that the relation between the eigenvalues there implies that this one-dimensional map is quite special in the sense that you have a discontinuity corresponding to the projection of the stable manifold. You see that here in this picture. This line, which is in the stable manifold of the singularity, doesn't return, of course. And then you have a singularity there. And the relation between the eigenvalues says that the derivative here in the left and to the right is infinite. And in this map, you can see that it's expanding, and the derivative where it is defined is bigger than the square root of 2. Okay. And studying this one-dimensional map, you obtain with this property and says that the maximum invariant set in the interval for the one-dimensional map is transitive, and then you carry this information to the two-dimensional map, and with this two-dimensional foliation, you carry all the information to the T-flow, and indeed you prove the conjecture by Lorentz. Okay, okay. Well, and then we have to inspire in this model to construct ours. Okay, okay, and then I'll start. I'll start here. You see that you have a let me see. A singularity. Here is the singularity. And this is the stable. No? I start with in a neighborhood is linear. Now the cross section is not anymore a rectangle, it is a cylinder like this. And you see that if you flow in a neighborhood here, you arrive to these cross sections, intermediate cross sections. It arrives like a pinched triangle. Remember that in the Lorentz, you have that let me just go back here. You see, it's the pinched triangle here. There, I am seeing this triangle, but now he is rounding. It's like a cylinder, pinched here, okay? Now, and the flow goes. This is the next picture. This is the beginning. The flow is coming, it's transversal to this cylinder. And then now I arrive to this auxiliary cross sections here. And I have to return. How I return? Okay, I start flowing from one side. But now I am on a three-dimensional space. Okay, I have space to go around and to return here. I go here, and then I have to return. Okay, I have space to do this. And how is this? This is the representation. You have the flow this picture here is the flow in this cylinder.
Could you explain where are the singularities?
The singularities is here. The singularity is in the middle.
And inside a cylinder?
No. If you could, okay, no. It's inside in the sense that, okay, you have the cylinder. Let me just see. You have like this.
The pink cylinder is transferred to the flow.
Yes. The pink, this is transverse to the flow. You have the part inside. And here is the singularity. Here, the singularity somewhere is here. Okay? And this cylinder here is like if you were in 3 dimensions. You have this. And then I have, this is the cross section here. But here I have another cylinder. This goes, no? Somehow. I have another cylinder here. And on the other side, I have another one. It's these 2 cylinders. And then the flow in the upper part comes when you flow goes here. I don't know how to draw better than this. And like something like that. And then goes around because you have the other part here that comes here and it's like here in the triangle.
Sorry, could you explain?
You see here?
What is the role of these new cylinders?
The new cylinder is just to make it possible to return it to the cross section here, the pink one, just to give it some orientation. Otherwise, I don't know. This is just why is it possible? It's a geometric construction that you can do it because it's possible to do it. In a sense that, okay, how I could say, okay, you are rear and then I return. However, I'm trying to explain you how it returns. Because it's in the intermediate, you have these 2 cylinders that will help you to return. You have the flow here enters this cylinder, and then you have to go out. Once you enter, you have to go out, okay? And then you enter here, you come, you enter the cross section, then it comes here, and then enters and else. Here is the picture that how you are returning from this cylinder to the cross section. What and this okay is what?
Sorry, the same T cylinder you have some closed orbit or not?
No, just this is the orbit is no, it's like a grid. That
around what?
Yeah, the orbits. The orbitals are like those. So look, these are the orbits. The other ones is just because you have to put I don't know how Diego made this picture, but he put some equations to realize this picture.
You don't have a closed orbit inside the cylinder.
No, I don't have any other one. The only singularity is this one, and all the other constructions. The point is that to make this beautiful picture, there are equations to realize that. You know, he has a program, and he put the functions there, and then flow it, plot the result. And that's why it appears this is like level curves of the function that he puts. Okay, anyhow.
Because in the construction of the geometrical Lorentz attractor, and those cylinders, you put them there because you have two eigenvalues, complex eigenvalues.
I'm not putting eigenvalues. No.
No. It's not it.
No.
Oh, okay.
Not
Thank you.
Not this. Okay, anyhow. And then now I'll look at this picture in another way. Let's see. Here, I have the cross section that I will split in the pink and the blue. And that is the image of the first return map. You know that this is an auxiliary cross section. And I'm looking, it's like a composition. The map, okay, you start here and then you go to this these two cylinders, and then you return it to this. You remember that you also have this kind of composition when you are constructing the Lorentz attractor. You start with the linear map. The linear map is from here to here. And then I have these auxiliary cross sections, one of each side. And then I return it to the original cross section. And the image is like this. You have that the image of each side here is like an essential cylinder. You know that it crosses all around. You have a pinch point here. Here is the corresponding to the projection of the flow in the central stable manifold of the singularity doesn't return. And then you have a pinch point, is the image of this point, the pinch here. When he turn like that, okay? Okay. Now, this is what I call the representation of a up Lorentz, in the sense that, okay, the pinch, like in the cross section, you can localize some region that contains exactly the usual image of a Lorentz attractor, okay, in the up part, and here in the down part, okay? And you see that, I don't know, but this kind of pictures suggests that when you move the pinch points from the essential cylinders, this is provoking all the changing in this picture, okay? Once, if you just push let me see here, the cylinder cross section, now I'm simplifying. I have a cylinder, and the cross section, I have the red part and the blue part, and the image are essential cylinders, and those are the pinching points of the cylinder. And all the dynamics that you can find, indeed, it depends on how these points are located in this cross section. You know that this corresponds to gamma plus corresponds to the intersection of the upper center stable manifold of the singularity with the cylinder. The green corresponds to the intersection of the down, the down component of the center stable manifold of the singularity with the cross section. And here you have these points. And what we have to study is to understand how is the movement of the pinching, depending on how you flow back to the cross section. Okay. Okay. And then indeed, all we do is to study this kind of map. You have the cylinder. Okay. Okay. I forgot to say that we can do that in such a way that preserving a radial stable foliage. Okay. And so we also can project this, and we have a one-dimensional map associated to this kind of map. And the one-dimensional map indeed is something like that. You have two singularities corresponding to the pinching points, or to the stable, how the unstable manifold of the singularity turn to the cross section. This is one singularity and this is another singularity. And one interesting thing is the following: from the one point of the one-dimensional point of view, you remember that for the geometric Lorentz, the usual Lorentz attractor, you study the one-dimensional map, and you have to require that the derivative where it's defined, the moduli, is bigger than square root of 2. Why you want this? Just to have that map is transitive, okay? Here, it's not enough. When you have two singularities, the type of the singularity is much the same as that one, because on each singularity you have that where it is defined, the derivative is bigger. And in the singularities, it's the moduli to the right and to the left is infinite. But you have to put to have a transitive attractor inside this, and then push it to the two-dimensional map and then to the flow. It has to be bigger than the golden number, because otherwise you have the risk to stay just in one side and not to cross to the other one. Okay, this is just a curiosity.
Sorry, this map is locally eventually onto also?
Yes, 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 yes.
Okay.
Yes, indeed, that's why you have to put this, the minimal expansion that you must have here is this, the golden number. The square root of 2 is not enough.
So why?
All right.
Why the golden number? Where does the golden number come from?
The golden number is the 1 plus square root of 5
I know what
over 2.
Golden number. Yes. But where does it come from? Why the golden number?
Yeah, because that is interesting because just we start doing the calculations, because what is the point? You have to have that when you take is to prove that this is locally eventually onto. And if you do you have an expansion, it's not so, it's like a small accounting that you have to do, and it comes for free, the golden number. And otherwise, if we start with one interval here, okay? You are increasing. If you don't put enough expansion, you have to come to this part. And the minimum that you can, this is connected with the size of the interval and the question, it's this one. Now, I don't remember that, Catherine, but it's there. But it's this. It was really amazing and nice, because then it's a little charming to the golden number. Next time I will try to remember how we get this and then to tell why. Okay.
No, it's just a mystery. Okay. There appears an...
Yeah, that's true. That's true. But okay. And then we have to understand what?
I think it's related to the fact that the golden number is the smallest Pizot number. And therefore, it's the smallest number such that the beta transformation is Markov. I think this should be related.
Ah,
but I don't
okay.
want to go into these things. Probably it is.
I don't, you know that in our paper there is a small lemma proving this, but I don't remember indeed.
Okay.
I don't remember. Okay, you have to compare. Okay, okay, I will not try to remember now because otherwise I will, okay. Okay, also moving the pinching points. And then you see that, look, you have the bread part of the cross-section here is sigma 1. Here, the blue part is sigma 2. And if, you know, the image of the sigma 1, if the pinch point is here, what happened? This is like, look. Now, look at this. This is the pink, okay? And then the image is like that. It's Markovian. Cross. Okay? Then you have that this cross, you should have a fixed point on the side. Okay? The same for the other part, for the blue part. If the pinch point is on the opposite part of the cross section, you have a fixed point here. Okay? But if you have a fixed point, then you have the stable manifold of the fixed point. Okay? And that is the next issue of this. Okay? And then the position of, if you take, this is the only that I will try to explain how the position of the pinch point with respect to stable and the unstable manifolds of the fixed point that arrive when you move along this picture, you see that in this position here, what happened? You see that, okay, you have the fixed point there, you have the fixed point, and then I will call this the component. You know that this is the stable manifold of the fixed point. This is the stable manifold of the other fixed point. And then the union of these two stable manifolds here, they split the cross-section in two components that we call plus and minus, okay? Okay, let's look at the component here. I just take one line here, L1 is a line above the stable manifold, L2 of P1, the red one, and the L2 is a line above in the upper part of this component. And I look at this rectangle here, okay? Look at that. Let me see. I don't know if you can see it. Okay. It's not so, I don't know. Let's see. Okay. Okay. Now, forget about the down part. What you are seeing. Look, you have here is this picture, no? Here. And also here, okay? It is continuous. Here was, then it's like they are cuspidal, no? Then the image of this, if you take this part and you look at the image is like, there is a classical Lorentz inside this point, this configuration here on this side, since you have the stable manifold here, they are invariant by the flow, okay? And since they are invariant, they are splitting, and you can look in this upper part of the cross-section as invariant. And what you are seeing is that the image, it contains a Lorentz, an upper Lorentz attractor, okay? Okay. And now I'll look at in the down part. Down part is respected to this lines and the stable manifolds of the fixed points, okay? Okay, this is the complement. And then what you are seeing, look at that. You have something, it's a Markovian. Look, you have this, okay? Here. And what you are seeing is this. Okay, what is this? This is a horseshoe. Okay, what you are seeing is a Markovian function map, and but it's far from this continuity, and indeed it's a horseshoe, but it's a fake horseshoe. It's not the horseshoe in the way we are used to, but it's a fake horseshoe. You can see just because of the orientation, it's like this. The image is a fake horseshoe. And then if you have this configuration and the position of the pinching points respect to the parts, the components of this. This means that the pinches are on opposite components of the cross section. You have the up and down loads and a horseshoe, a fake horseshoe. Okay. Okay. Then there are more situations. You can see when the position is like this, for instance, you have that the two pinching points are in the same side of the cross sections, then you can prove that it arrives at what we call a two Lorentz attractor. Why? Because you start to iterate any interval here. You notice that the stable direction here are radial directions, okay? And the unstable directions are just transversals, like following the cylinder. And if you start to iterate any unstable segment, it will accumulate on all the image. And in particular, we will accumulate the stable, century stable manifold of the singularity, the up and the down, okay? And this is the way that when two-sided Lorentz attractor appears, okay? You have another situations, for instance, homoclinic loops. Homoclinic loops arrive when, let me just, you see, the line here, the magenta line is the stable manifold of the singularity. And the pinch point, one of the pinch points is just in the touching this stable manifold, but this corresponds to the unstable, and then you have a homoclinic loop here. You have other possibilities. I'm just putting here all the possible the homoclinic loops. I don't know what happened there. And okay. And in this case, you have a two-sided Lorentz attractor. It's just, again, you start iterating unstable segments, and you approach both center stable manifold, the up and the down of the singularity, okay? Okay. You also have a collision of Lorentz like attractor and fake horseshoe. When you see this, you can have heteroclinic loops, no? This occurs when you have the pinch point here, no? This always corresponds to the unstable manifold of the singularity, and it falls in the stable manifold of the fixed point here on the other side, because you see that this is the case that the pinching point of the red is on the blue part of the cross section. Then you have a fixed point on a red fixed point, and the unstable manifold of the singularity falls in the stable manifold of this point. This is an heteroclinic loop. You can have it too. No, you have this fixed point. Maybe you can you have two. You see, the other pinching point is also falls in the stable manifold of the other fixed point in this configuration. And then you can see that in this case, what you have is a full Lorentz attractor. Just studying the map like this. Okay. Again, here is in a codimension 2 manifolds, because you have that the two pinching points fall in the same component of the center stable manifold of the singularity. And then, okay, you can prove that in this case, both unstable, I think, okay. You have a fat Lorentz attractor. You see that here, how you see this? Just forget about a small piece here, okay? And then it's going through all the cross-section and closing here. It's a full Lorentz. In a sense, it's the representation of this in the one-dimensional case is like that when the one-dimensional map fixes the zero under the one. But anyhow, then you have a fat Lorentz attractor, because in the sense that it crosses all the stable leaf of the attractor, cross all the stable leaves of the cross sections, okay? Okay. We also can just, you have, in the case that you have an intersection of two, a configuration corresponding to the intersection of two heteroclinic loops, we can study how is the unfolding of a one-parameter family crossing this point, and this is the configuration that we found. This is a local configuration, okay? Okay, there are other situations that anyhow we can describe everything that can occur in this construction, and give you all the situations that correspond to a up, to a down, to a fat, to a full, to the horseshoe, to a fake horseshoe, to the collision, to the merging, etc. But I will not announce any theorem because it's too complicated, but the point is that we have this description of this open set of flows in R3, presenting all these kind of configurations about the Lorentz attract to up, down, two-sided, and a fake horseshoe together with a fat Lorentz, etc. Okay. Okay. That's all about mathematics. That, and the proofs are already we uploaded the article in the archive one week ago, I think.
Zezé,
okay. Wow.
Zezé, maybe if you allow me, I would stop a second for see if there are questions about this part.
Okay.
So, okay, there are any questions? Someone wants to make a question? Your last chance. So if not,
last chance.
Okay, if not, so let's pass again to Zezé.
Okay. Okay.
Is this? Can we consider this the part where we start to drink?
Okay. Not yet.
Okay.
Yes.
No, but this is water, huh? This is water that I'm drinking.
This is not the water. Well, it's hard to see.
Not yet. Not yet. Let's wait just a bit more, please.
Okay. Okay. Now, I will start with the second part. The second part, I will comment about the evolution of our program through these 50 years, pointing out some highlights, factors that, in my view and the opinion, lead to the academic excellence achieved from the late to the 80s. Okay. Okay. Then. Okay. In the beginning, from the 70s to the year 2000, you know that the coordinator of the program was indicated by the direction of the institute. Okay. And in 2000, the people in the pro-rectory of research at UFRJ. UFRJ means Federal University of Rio de Janeiro, by the way, forced the program to be administered by a commission and a coordinator elected by the professors. Then, the end of the era of the coordinators appointed by the direction. At the same time, CNPq, which at that time was the largest scholarship financier of our program, started to direct master and doctoral scholarships directly to the researcher. Then this opening in the program's line of research, previously predominantly analysis and the partial differential equations. This is just one point that I would like to clarify, because in the beginning, the strongest research group there was on analysis and EDP. We had big names as in the beginning, like Leopold Nashbin, and we had also Luis Adalto Medeiros, and they were, Luis Adalto also is on EDP. And with, since the coordinator was indicated by the direction, it always, the choice was always one of the people in this group. And then it was quite concentrated, okay? And these 2 points here changed I think that this was like how you call this, divisor de águas, water divisor in this year, okay? Okay. And
Turning point. Turning point.
Turning point, yes. Under the coordination of Valci Santos, in the period of 2003 to 2007, you see that that was, I think that she was the second coordinator out from the PDA. No, I think that the first coordinator of the program out of the research group on analysis and EDP. And the following actions were implemented. First, the formulation of the teacher's profile and the program regulation. And this was a faculty renewal. And the union of the applied mathematics and applied and the mathematics programs, and then strengthening and coherence in the objectives of the program. And as a consequence of this, in the 2007, the program achieved Note 6. I have to explain that this is, you know, that we have the capacity coordination for postgraduate programs in Brazil, the agency, the major agency responsible for the education and this in the universities is CAPES, and there are 3 years, each 3 years there is one evaluation for CAPES, there is a coordinator of the area, and there is an evaluation independently of the universities, and they made a rank between the universities and the programs, not the universities, the programs. And you have from grade 1 to grade 7, 7 is the maximum, okay? And then this year we got this, the grade 6, almost the top, okay? Okay. And as of 2007, we have other coordinates, but we remain steadfast in the pursuit of academical excellence. And in the last 2-3 year evaluations, 2013 and 17, CAPES gave us the maximum, which is Note 7. This is like a certificate of excellence, okay? And you know that in Brazil, I think that we are 5 or 6 programs with this grade, among the many, more than 30 programs. I think that we have 50 programs on post-graduation. Graduate programs, okay. Then we had another problem, how to pass the lack of students. Because you know that in Rio de Janeiro, Rio de Janeiro is a special city. You know that we have 4 institutions very strong on mathematics. You have the Federal University, the INCA, PUC, Rio, Catholic University, and the Fluminense University, it's across the bay in Niterói. Then you have to, how you say, disputar? To compete. Now, we have this point. Another point is that Rio de Janeiro is, as we were talking before the talk, it's an expensive city, no? Then in general, I think that the student would prefer some other place with housing and living cheaper than in Rio de Janeiro, anyhow. Okay. But then from 2012 on, we introduced together jointly with the graduate program of São Carlos, the ICMC, UPS, State University of São Paulo in São Carlos, the extramuros test select, oh meu Deus. To select them. Meu Deus, meu telefone está assim, desesperado aqui. Bom, então, me desculpem, eu tenho que desligar isso aqui, senão não vou ter paz. Pronto, ok. Then we introduced in 2012 this kind of the extramodus test, and today extramodus has 25 application centers in Brazil and 13 in Latin America. And this again, it's another turning point. We start having more students, and not only us, because we have much more students, I think, in many other programs, because no. And the consequences of this was that the average number of graduates increased to 20 per year altogether, in master degree and the PhD degree. And the first postdoctoral fellowship was in 2005. As of 2008, we count around 30 postdoctoral fellows at our program. And during the 50 years, we had 150 PhD graduates. 180 are from 2007 on. You see that that was really a turning point. All this, I would say that these three factors now were fundamental to our program, just to go around and to achieve the excellence nowadays. Okay. Okay. And now, events. Another thing that you can tell about the program, okay, you have the professors, the faculty, and then you have the students, you have the graduates, and then you have the events that you organize in your institution. This is another, how you call this, that measure, I don't know the English word, how to say, but it's the quality of the program. I don't know how to say this, and all
Say em português.
O que eu quero dizer é que o fato de você organizar eventos que não só por professores, isso nós temos muitos professores no nosso programa que organizam eventos que são realizados em outras instituições, e isso é um sinal também da internacionalização e do reconhecimento, né, da qualidade da matemática feita no nosso programa. Mas os eventos organizados e realizados no nosso programa é um adicional a isso, entendeu? Que mostra que you know that I'll turn on now. This is in addition, because you have that people coming to our university. This is different than you go to another university, you know. This is a kind of recognition of your institution as some place where research and quality of good quality is going on in your institution. Is this what I mean? Okay? And then I try to, it's a shame, but I don't have many records outside of dynamical systems. And I collect some, and I'll show the poster of each one in chronological order. This is, I'm going to the third part of my talk, okay? Okay, and then, okay. The first two events on dynamics was in 85 and 87. At that time, there was no cell phone, no internet, nothing. And I don't have the poster. This is just the program that I put here. But you know that we had here quite Jean-Christophe Yokos was a speaker, and also Maguire, Robert Rosari, Clark Robinson, and Hank Brower. And we even have a proceedings of this meeting that was organized by Maria Isabel Camacho, me, and Flores Stackens. Flores Stackens was also here, Flores Stackens. And by the way, Flores Stackens was a great friend of our institute. Anyhow, and it was quite interesting. During this year, what happened was that it was so amateur, how is this? Not professionally organized. Because you see that the year here is 85 and 87. Why? Because during this year, there was the Brazilian Mathematical Colloquium at IMPA. And then you see look here, when August 27th, we profited from the people that was coming to IMPA as visitors there. And then Maria Isabel and me, we were there at IMPA with some piece of paper telling, okay, we have this kind of program, distributing to people there at IMPA. And we met in a square nearby my home, and the people from IMPA, they always help us on this issue. Everyone was giving a hide to someone to go to the Federal University, because at that time it was quite difficult to arrive there. Anyhow, but we could do, and we have a the program was quite nice, and we had great names there. I will show you the pictures afterwards. Okay, and then we had the next. We had we had a course, expeditions to the UFRJ, because Rafael Duadi in 86, he was given a course at the UFRJ. I invited him to 1 month there in the university, and there was a course on celestial mechanics. And then we were you know that in the picture, it's not too clear, but everyone here is from IMPA. And from the UFRJ was, here is Mário de Oliveira. Maria Isabel Camacho was always a friend of mine, and she organized everything with me, and me. All the other ones, no, Luis Carlos Guimarães is another one, okay. 4. The other ones were from IMPA. Here you have Marcelo Viana, Lorenzo Dias, and Christian Bonatti. This is o Duadi pai. How is the... Qual é o primeiro nome do Duadi? Adrian Duadi, César Camacho, and you have Rafael Duadi, Jacob Palles, all the other ones. I think at that time there were only Maria Isabel Camacho and me. We were the only ones on dynamics at that time. Okay. And then we organized in 89 and 91 another 2 meetings on dynamical systems. Again, I don't have any poster, just the program, and you can, I don't know, but here we have again, Takens, Benedictus, I cannot, Josephine Finn, Newhouse, Sinai, Zender, Eddie Zender, Jean-Christophe Yokos, again, o Dennis Sullivan, o Moser was also at that time. In this colloquium, Michel Leman was also there. But it was quite interesting anyway. Then this is one of that I could collect. I cannot, how I do to diminish it. That was in 96. This was to celebrating the 70th anniversary of Luiz Adalto da Justa Medeiros. And then I collected 2 more on geometry. I don't know what's going on with my tablet that I cannot diminish. I don't know how to do this. I don't know. And now this was, I cannot see the year. How I
think it's 2005. And
2005. 2005. It's marked here. Okay. And the other one, I don't know. I think that's 2007. I'm not sure. Maybe here. Okay. And then, no, how I didn't. Como eu faço isso? Someone could help me on this because I cannot move in my tablet. I'm trying to.
A Zezé está no Samsung. Alguém sabe como expandir a tela, diminuir?
Não sei. Ninguém can help me. No one can help me, no.
Se você clicar no lado esquerdo do seu, como chama, do mouse touch, aí aparece no meu computador é assim, aparece uma telinha onde você tem um zoom. Vê se tem o seu...
Deixa eu ver. Não sei, refazer? Não consigo, cara. Não tô. Eu tô rabiscando.
Não.
Deixa eu pegar a borracha. Olha, eu acho que ele impactou aqui. Ele congelou em algum lugar. Não consigo.
Talvez se parar de compartilhar e compartilhar de novo.
Isso.
Pode ser, exatamente.
E agora sim. Como que eu vou parar de compartilhar, hein? Vixe, Maria. Olha aí, ele congelou. Deixa eu ver.
Acho que a gente pode tirar, Jaqueline, eu acho que isso.
Sim,
eu fiz.
Pronto.
Zé, fiz.
Tá, agora eu vou...
Aí conserta aí e depois reconecta.
Deixa eu ver, deixa eu tentar compartilhar. PDF. Olha só.
Tá bom.
Não consertou.
Sim, mas você conseguiu fazer o zoom, não?
Não.
Então, antes de compartilhar, tenta fazer o zoom.
Tá, então interrompa aí de novo, por favor, Jaqueline, que eu vou tentar mexer no...
Pronto.
Deixa eu... Oh, meu Deus.
It's okay, Zezé. Technical problems.
Let's mas aqui não... Eu não estou conseguindo fazer.
Não?
Enquanto isso, bebendo.
Isso, Daniel.
Não é salvar.
Yes. Very good, Pedro.
Tenta fechar o programa e depois abrir de novo.
Deixa eu... Olha, eu vou te contar. Vou
buscar o meu também, Pedro.
Vamos todo mundo começar.
Se não, deixa assim mesmo. Deixa assim mesmo.
Aqui, agora ele está rolando, salvando. Quem disse que eu quero salvar?
Agora, peraí, que eu vou buscar o meu. Peraí.
Eu não quero salvar nada. Como é que eu interrompo? O Sérgio está aí? O Sérgio que é o...
Sérgio tá, Sérgio.
Como é que eu faço essa porcaria aqui? Eu vou te contar.
Calma, CC, calma.
Pronto. Aí saiu tudo. Deixa eu ver. Ai, carregando. Pronto. Agora parece que ele vai. Deixa eu... Agora, o que eu tenho que fazer mesmo? Tem que entrar na reunião, né?
Você carrega, mas não ativa o áudio.
Tá, não, aí sim, tá bom.
Agora aí não ouvimos os palavrões que você disse.
Compartilhar, tela,
Quero ouvir os palavrões.
PDF, pronto. Tá. Então, deixa eu voltar para ver foi 2005 and 2009, the geometry events. And then in dynamics, we had in 2011, partial hyperbolist in the EMF of UFRJ, and then 3 days, a week on dynamical system, and then probability and dynamics in these years. And then in ADP, in partial differential equations in 2019 and 2020. And then the 3D dynamics, I couldn't take the picture. You know that the data here is 2021 because I couldn't take it last year. I don't know why. Because when we click that,
it disappears. Have to fix it.
Okay. And then some participants of these events that we have here: Levovix, Moser, Sinai, Nakarian. This is Marmi, Stefan Marmi. Here, Ricardo Mayer, Marco Martins, David Ruel, Michael Benedict, Sheldon, Newhouse, John Franks, Lyston Young, and this I don't know. I lost the. Here we have again Jacob Pallis, John Matter, Plácido Tábuas, from São Carlos, Sérgio Plaza, Angelo Baroni. This is Nicholas Kuiper, Yasha, Sinai, Flores Stakins, and Dennis Sullivan, Ruel, Katok, and here Robinson, Rosari, João Franks, Jean-Christophe, Paulo Sade, Fred Dumortier, and again a group out of Katok, Wellington de Mello, Klaus Doring, João Fernando da Rocha, Ed Zender. The other ones, this is Júlio Canille, at that time a student at IMPA. And here is Mário de Oliveira, Maria Isabel Camacho, Mark Poliquot, me, Luiz Carlos Guimarães. Here is François Ledapierre. And now it's all the same people, more or less. I'm just passing without telling you the names, unless it appears someone.
Ice cream, coffee break? Did you guys serve ice cream?
Yeah, no, you know, at that time we took that was in the break. Everyone was with ice cream. You know, that's having an ice cream. Again with the ice cream. This is Marcelo Viana, Klaus Doring, César Camacho, Paulo César Carrião, Júlio Canille. This is Shiraiwa, Charles Pugh, Lyston Young. This I don't remember. François Ledapierre, Bodil Branner, and this one I don't remember. And
wasn't that Sergio Finley on the last slide? Was that Sergio on the last slide?
Was what?
Is that Sergio next to Ladrapi?
I don't think so.
It looks okay.
I don't know.
Between Lysine and other side. No.
Could be Jörg Schmeling, I think.
Oh.
This one?
Jörg Schmeling.
Schmeling.
Yes,
Yeah,
yes, it's
yeah,
Schmeling.
that's
Yes,
you.
yes.
Ah, yes, it's Schmeling, yes.
Oh, Lorenzo, do you remember who is this one? The bound one? I don't know.
I don't know.
I don't know. Anyhow.
Schmeling, for sure.
But here, the interesting is the following. You know that in this picture here, you have Wellington de Mello, me, and this is Daniel Panazzolo. Daniel Panazzolo was my first student, his master, in 2004. And here is Hermano Fried. And again, a group, Sheldon Jacó, John Frank, César Camacho, David Ruel. And here behind is Edson de Faria. Okay. This is the list that in this course of in the Federal University by Rafael Duadir. And now we have big speakers there, distinguishing. And that was Cédric Villani was there. And also Etienne Gis. Etienne Gis gave a talk there, a wonderful talk about at the time of the World Cup there in the Federal University. And this is Lawrence Evans at our institute. I think that this is almost. Finally, we arrived to the end, almost to the toast. Congratulations. Okay? And it is still I get emotional.
It's okay.
Breathe.
There is no other way.
Okay.
That's making you yourself. So.
Okay. You can read what I want to say.
Okay. So
You can read instead of me, Jacqueline, please.
Okay, I'll read. Zezé words. So, congratulations to our graduated program for its 50 years. It's still a young program compared to programs around the world. But the research of its professors over the years has shown its strength, not only in producing packed results in its different research lines, but also in the training of excellent students who actually actively participate in the graduate programs, not only in Brazil, but also in Latin America.
Continue.
Okay, from now on, the responsibility for advancing further lies in the hands of its youngest researchers. Oh,
your
responsibility.
Yeah,
not me.
No, you. And then my vote of much success to you. Okay?
Thank you, Zezé. Thank you.
Thank you.
Thank you very much.
So let's. So let's do I have my help here to do the toast. I would like to open some sparkling thing. So I invite everyone to have your glass.
I think that it would be good to everybody who can open its video. Yes, video camera.
Stop there.
I will stop.
I'll do it for you. Stop the show.
Yes, okay. Yes. Thank you.
Okay.
Parabéns. Congratulations.
Congratulations, no have.
Congratulations.
Congratulations to our program indeed.
So I ask everyone that can to put the camera so we can make a picture.
Take a picture.
So, well, let me get ready. Everyone's there. 3 seconds. 3, 2, 1. Maybe another one because
another one because you know that since I am one.
I'll take another one if we're ready. 3, 2, 1. Okay. Yes. I will take another one because we have 2 pages. So
yes, the other page, yes.
Everyone has to get ready. Okay. So in 2 seconds, 2, 1. Thank you. Thank you. Thank you, Zeze. We didn't thank her for the talk and for the very good, beautiful story of our program. So thank you.
I hope you have it like also the part about mathematics. You cannot
So I would like also to thank all the speakers for these days. I really think that summer it's time for learning, and I always regret in the middle of organizing anything because it's work, and then you think I should have done, but in the end it's always very good. And these 3 days were very productive. I have learned a lot. It's not easy to give talks. It's not pleasant to. I know that you don't get too excited. I have to go to Rio. It's one thing. I have to give a talk online. It's another thing. So for this, I thank even more for you that accept for this. So thank you all the speakers. So I hope that we can do another applause for all the speakers. And thanks my colleagues that helped to organize too. Luciana Salgado, Alexandra Vieira, Gaia Soli. Thank you. If someone is in the audience and would like to say anything about our program, so the floor is open. You can speak.
So I would say thanks to the organizers of the event.
Thank you, Pedro.
Thank you.
Wow. In the name of the participants.
Yeah, of course, sorry. All the participants.
No, I have to. We have to. You organizing committee.
You must wait. We take a little drink, yeah. First.
Yeah, okay. Let's toast it to the organizers. Yes. And then, I know that how you have to do a lot of work to organize any event, even if you're online or there or whatever.
Oh, yes.
And it was quite interesting, very good talks on the friendship ambience and amusing. Thank you. Thank you. In the name of all the other ones.
The other.
Yeah, okay.
Well, just hope the next event you are going to have ice cream.
Yeah.
Maybe açaí, Daniel. Maybe açaí.
Açaí we all have.
Even better, yeah.
Açaí we always have, but we can think about ice cream.
Oh, yes. This is a very good idea.
Everyone there with the ice cream.
This is actually a very bad idea. It's 10 degrees. It's 10.
Why?
Minus 10 Celsius outside, right, Dobby? It's cold. It's snowing.
Okay, a hot chocolate. Okay.
I don't know. Have you ever tried to have ice cream in Rio? This is practically impossible because they are melting so fast that you really have to eat them immediately. And now I don't know, in Chicago and here in Krakow, you can go and have your ice cream for hours and they will not melt at all. So yeah, there are certain advantages of low temperatures, but yeah, let me just say well, a few words because I feel kind of partially a graduate of this postdoctoral program at UFRJ, and there's a complaint that the program is young, and well, I can tell you that there are great advantages to that. Well, jokingly, really, well, at my university, we have mathematics since 1400. So, but the question is, but at that time, of course, there was no program. And actually, we are so old that we cannot reasonably celebrate any anniversary because we cannot tell when it started. So this is one thing which is nice, because like first PhDs were granted just in science without division in mathematics or whatever. So we can't even say, well, one can decide on the title of the thesis. And the second thing is that working for a young institution is great, because in all the institutions, everything is a tradition. And if something is a tradition, then you cannot change it. And working for the young institution is great because you can shape it as you wish. And nobody will tell you that, oh, this is a 200 years tradition, so you cannot. And finally, which I really find great is that you can wear your flip-flops, although I know that there's complaints when Manuel wears flip-flops PhD defenses, but I think this is actually great, because at my university they made us wear this Harry Potter robes and you know, we really have to at the granting the PhD diploma, we have to speak Latin, which is
oh my God,
which is awful. So and here you can come to the defense with a T-shirt of your favorite football club, and this is really great. You don't have to dress
Wellington, like Wellington.
Like Wellington, exactly. That's the point, and it's really, I think this is wonderful. So yeah.
Yeah, each one with its particularities, you know. Yeah, that's true. I remember Wellington was with the Flamengo t-shirt.
Really?
Yeah.
But that's a very dangerous
I didn't.
thing.
I'm a
dangerous thing, because if you have to make sure that you know the committee teams before. Because imagine if you go with a shirt to defend your thesis and the committee has someone that is in the opposite team. That's a danger. That it's really to trust in your thesis. You have a very good trust that your thesis correctly.
Very good. Yes, I'm a former from UFRJ, and I'm very proud of it. Very proud. It was a dream for me. Oh, nice. I can't speak very much because I'm emotional too, and but it's really good for me right now to be professor at UFRJ. After I was a PhD student, and okay, it's all right.
Yeah,
I think that is all. I was a student from Alexander, and Alexander say everything.
No. Is that I think that it should be worth to note that most of the successfully of our program also is in part to the students. They are really hard worker students. So I think that for us there are professors, so it gives you some boost to teach many theories that it's not too common to give. So we give some lectures and it's funny, you know, it's fun, really fun. So because we know that they are really working hard. So.
Well, by the way, you know that Alexander was the first postdoc student there in 2005. Yeah. Under the advisor of Valci Santos and me. We made a project to campus, because you know that once you have your evaluation is good, as 6 or 7, then there is a possibility of the program can have could, because now it's a different situation, but the program would for 5 postdoc students that we could have a year, per year, no?
Whatever postdocs before, it was just organized.
No, that was, of course, no. Lorenzo was.
Would you say that 2005 there was the first
I don't know, but no, you know that I cannot speak too much. You know that.
The famous Barca was the student.
Okay, postdoc. Lorenzo Dias, Rafaela Baca, Mário Jorge Carneiro, Henrique Pujaus, Carlos Morales.
Lorenzo Dias. Me too.
Luciana Salgado. You know that since the beginning, Rafaela Baca, Lorenzo Dias, it was in the 90s, you know. But what I'm telling you is about the new times, no? In 2005, because all the other postdoc students.
I have the new times.
I just want to say that you don't count. It's like
I know that is something else is there.
Now that was you know that the point is that the program was for postdoc was different. At that, Alexander was the first one for CAPS. Before that, we had the program together with FAPERJ. It's another agency, a local agency in Rio de Janeiro. And the grants were from FAPERJ. And we had all these people there, Lorenzo Dias, Henrique Pujaus, Carlos Morales. Álvaro Rovella. Quem mais me lembra aí? Eu estou perdendo um que eu não me lembro agora. Rafael Labarca, Rodrigo Bamon. I think that all the students from IMPA that completed the degree around the 90s, they went to the UFRJ, maybe, or many at least. And it was always under my supervision. And Lorenzo and Álvaro, we were in another department that we had a fight there. And then, yeah, but anyhow, yeah. Indeed, you say that it's a shame because during all my life, I think that I have more than 20 or 25 postdoc advisors. Isaiah was one my fellow, and Maurizio Monge, Luciana Salgado, and there are many of ones here. That, but it was quite different, the situation. It was another thing. We had that was like a project that we did to FAPERJ. And the name of the program was like, the intention was to give I forgot the name. It was not a postdoc fellowship. I forgot the name. But anyhow, I had many. I think that George Belloc was also a postdoc student of mine. He spent 1 year there at some time because George Belloc and me, we made the same contacts to the Federal University. And then he was the first classified, and I was the second one. And there was only one position. But then he decided to go to São Paulo, and then I was absorbed in his place. And many years later, he spent 1 year there at the Federal University, and we were working together. At that time, we have a paper on saddle node bifurcation, if I'm not wrong, and we developed there during that year. I don't remember the year. At the same time, during this year, George Belloc was there, and also Rafael Labac. Rafael also spent 1 year there. And there was one time that we were trying to convince Mário Jorge Carneiro to come to our university. But unfortunately, no, they went back to, because Mário Jorge was in a postdoc program at IMPA with Jacob Pales. And he was spending that year there at IMPA. And there was a possibility of contract someone to the Federal University out of this kind of contacts, a visitor, professor, some position that appears suddenly. But Mário Jorge, okay, he stayed not a short period there and went back to Belo Horizonte, where he is working till now. There are many stories like that. Another one is Rodrigo Bamon. Also, he spent, I think that Rodrigo was in a position as a postdoc directly from the Federal University, not from CNPq or any other agency. And okay, I remember I was working with him, and I would like that he was contracted there, but he didn't accept at that time. And Rafael Labac was there many, many times. And Rafael was terrible, because I remember that we went there all the time. I gave a ride, to him every day to go to the Federal University, and he was, let's go back downtown to IMPA, whatever. And we had another visitors there, Fred Dumotier, Flores Takens, and it was interesting because at that time it was hard to stay in the Federal University. And then people, we had to make an effort just to stay there, Can you imagine that the air conditioning in my office, Maria Isabel Camacho and me, we bought the air conditioning. There was no air conditioning there. And it was hard to stay there. And the classroom, the offices, and everyone, another time. Now it's much better, much better.
We still have the smell, but actually it's a thing. I recently passed by car near to Fundão, and when I was approaching, I felt some kind of missing the space of work, like, oh, this is, I recognize the smell, and then I felt, oh, I'm approaching Fundão. Well, everything is it depends on the reference. Since we don't go to the campus for months, it's even the smell of the...
No, but you know that there is well, I have an interesting story. I don't know what does it have to do with Fundão, but in some sense with the smelling. Once I went to São Paulo in the interior, my hometown, Guariba, with Laura. Laura, my daughter was, I don't know, 3-4 years old at that time. And that my city there in the interior of São Paulo is in the middle of sugarcane plantations, and there are many factories for sugar and the álcool, whatever. And you have to go to Ribeirão Preto, and from Ribeirão Preto, usually my family take me with the car, and we go to Guariba. And once we were just passing through one of these factories of alcohol, and Laura asked me, are we in Avenida Brasil? Because of the smelling, because the smelling of in the place where they do alcohol and sugar, we call usina de cana-de-açúcar. No? There are big, in that region, there are 4 big, the biggest ones in Brazil and in Latin America. And the smelling is horrible. Much worse than in Fundão. Much, much worse. Anyhow, that's life. Now it's completely different. We have here, yes, okay.
People, I gotta go because I have another compromise at 7 p.m. and I have to prepare about it. This is the World Social Forum, and I'm a part of World Social Forum.
Ah, okay.
Yes, Fórum Social Mundial, and I have a compromise of this. I'm a, como é que diz apresentar? Vou apresentar pessoal da Bahia lá. I'm going to present a people, an artist people there, and about Abaeté, Bahia, and Parque da Fonte, São Paulo, and I have to go to prepare my my talk.
Your speech.
Yeah, speech. Okay. Thank you everybody for coming, and thank you Zezé for the words, and everybody who speak and Jacqueline, because she is the head of this workshop. And okay, thank you very much.
Thank
Bye.
you. Good luck.
Bye.
Bye-bye.
Bye-bye. Okay, now I think that I am also lying. I have many other histories. Otherwise, I can stay here talking forever. This is horrible. And then someone will accuse me, you talk too much. What can I do?
Não, você não fala pouco.
I also talk too much. I think it's impossible. So it's part of characters, cannot change.
Yeah. But it's a pity that Lorenzo didn't stay in my university. At some time he decided to go to Catholic University.
So try to convince also.
Sharing an office with you is not for me.
Yeah.
Sorry. I think that cutting is
This is only for the toughest.
For the very brave people, I think.
Yeah, very brave people.
Very brave people.
Yeah. That's true. Anyhow. That's true. Okay.
Então tá bom.
Yeah. Yes, we see. At least we see you all at Lourenço's Resistência next month. Next month? March. March is next month. Not March?
Lá, o Lourenço não está escutando.
The first meeting will be on 5 March, I guess. That is the first Friday of March with Vivian Baladi, Natalia Jurga, Amy Wilkinson.
Great.
But let me also say that I'm really happy to participate in this meeting and see how all these people of the Federal University, you know.
You are one of the first ones, Lourenço. You know, we're getting old. Yeah.
Bye-bye. Thank you, all speakers and organizers. See you soon. Bye-bye.
Tchau, Pedro. Obrigada.
Yeah, obrigado. Obrigado, Zezé.
Tá. Tchau, um abraço.
Até breve.
Tchau.
Um abraço pro frio. Tchau.
Yeah, Dominique was complaining about the coldness there, but right now I'm dreaming about this snow that you have said. I like the summer here. It's good. We have good weather, but it's a bit too much now.
Snow is okay as long as you have snow and below zero. It's okay, but the worst is like when you have something in between. So below zero at night and on above zero during the day, and then you end up between ice and mud, basically. And
you know, it's like the ice creams in Rio. It's the same thing.
Yeah, exactly.
The similar situation.
Unfortunately, not eatable. So it's the bad, but the description is very accurate. It's like it's completely crazy. Yeah.
We are burning here. You see that during the day we burn, at night we have to put the air conditioning, and then we are freezing inside, and then go out. It's again.
I know, but you know, I still would exchange. It's like I can tell you from those.
I'm with you, Dominic. I'm with you. I would also exchange.
Yeah, it's like ask Gladstone, ask Alexandra. They are. I think that they probably suffer much more than I do. It's.
Yeah.
I prefer the winter than the summer in Rio, definitely.
Yeah.
Summer in Rio, hands down for me.
Davi,
I think we just have a few days that is really bad. Davi. The other time is fine.
Em Chicago, Davi?
Yeah, sim, tô em Chicago.
Tá bem frio aí, não?
Eu achei que ia estar pior. Yeah, I thought it would be worse, but what makes bad here is the wind.
The wind.
Yeah, sometimes it's even hard to cross the street because of the wind. But I mean, I stay home most of the time, so I'm okay.
You know that I am in Búzios, and the wind here is also, but it's warm.
Zezé said this just for throwing on our faces that she's in Búzios.
I agree.
Everyone jealous. I can say that I am, Zezé.
Yeah. Oh, my goodness. Yeah, because you know that the trees here, the tree here, they have some inclination like that. There are many casuarina. Casuarinas is a type of pinus. It's not a pinus, but it is from the the same family. And because of the wind, they are like that. They are never erect. It's interesting. Anyhow.
I wish for a bit of this wind. It's not the here. There is not. These 2 last days were a bit worse, but I imagine that in 1 more day it's gonna be back fine. It's okay.
Yeah. Now I found the, how you say, sorry, Lorenzo. Call Lorenzo, because now I found the justificativa. How you say this in English? Justification.
Explanation.
Explanation. The explanation why I didn't talk about the postdoc fellows from the past, because I was talking about the 2 last decades, from 2000 to yeah.
But there's only CAPES postdocs they count. The FAPERJ postdocs they don't
count. Another reason. Another reason. Another reason. Yeah.
Guys, I will have to go because you know it's one of the things I acquired during the pandemic is 2 dogs. And it's high time for us to walk. Maybe you've heard them because they are sometimes in the background complaining about things. But I would like just to say that you know we are talking about we have been talking a lot about institution, and institutions are important, but well. You can give a lot of work and you can do a lot for an institution, and well, let's be frank, institutions very hardly ever they give you that back, because institutions tend to be quite not human, not welcoming, but well, for me it is always that people are more important than institutions. So I would have to say one thing that maybe I wouldn't do much for the PhD or graduate program at UFRJ as an institution, but I think that for people working at that institution, that is like a completely different story, and this is some kind of a community which is very nice to see from time to time, and to feel a little bit as a partial part of it. It's a super great experience. So thank you for allowing me to do that, and yeah, enjoy
Thank you, Dominique.
Enjoy your stuff, but okay, remember that this is you who really create this thing, not the kind of abstract institute. So yeah,
thank you.
And then sorry, I have to be going till next time. See you. Bye.
See you. Bye.
Sure. Bye.
See you. Bye.
Oh, we also have to go. We have some other things planned. Well,
okay.
Muito obrigada. Parabéns para o trabalho feito.
Obrigada.
Hopefully 51, 52 at most. There will be another celebration.
Okay.
Well, Catherine, thank you for you too. You are a big part of it. I wish you could have speak a bit. I invited you, but unfortunately you couldn't. But maybe in the next.
My internet is also
Yeah, I know. So just acting.
Yeah. Okay.
Bye.
Yeah. Let's go.
Thanks for organizing.
Okay.
Thank you, Jackie, for the organization, and for and to all of you for being part of this great institute. Thank you, Cece. Thank you, Alexander. Thank you, Catherine. Manuel also. And Jackie.
Gabriela is another postdoc student there.
The most recent.
Yeah.
The current as postdocs.
But I only have 2 days there because of the pandemic.
Oh, okay.
Yes, I arrived and then start the pandemic, and that's okay. I need to work from my house.
Sorry? Português, hein?
Agora
se for falar
português. O Stefano aprende tudo.
O Stefano fala português. Ótimo, ótimo. Eu também, mais ou menos.
Aqui Quem é o Davi que está aí? Desculpa, é o Davi Paternai? Qual Davi que é? Tem umas pessoas que eu não... Davi, não me pôs o sobrenome?
O Obato está aqui, mas tem Davi meio dele.
Davi tem uma D no final.
Tem uma D? Então não é.
Tchau, tchau, Lourenço. Tchau, tchau.
Tchau.
Tchau, tchau.
Tchau, tchau. Let's go. Okay. Now the real toast. Tchau.
Eu ainda tenho que terminar.
Eu não peguei nada, eu estou com água. Água, limonada. Olha aqui, ó, pastilha para garganta. Nossa, assim tá.
Nossa,
agora
tome um vinho no fim do dia, que você merece.
Agora no fim do dia, sim. Tchau.
Tchau, Zé. Muito obrigada.
Nada, tchau.
Tchau,
Tchau, pessoal. Bom vê-los todos. Cada lugar diferente, com frio, com calor. Né? Obrigada, Davi. Foi ótimo. Um trabalhão, mas fez um excelente trabalho. Obrigada.
Obrigado pelo convite. Eu vou almoçar aqui, que já é 3 da tarde e ainda não comi.
Coitado. Vai lá, Davi. Até mais.
Um abraço aí para todos.
Tchau.
Abraço, Davi.
Tchau, pessoal.
Tchau, pessoal.
Tchau.
Tchau, tchau.